Lesson 4.2, relationships between lines on the plane. This is also known as systems of equations. When more than one line is graphed on a single coordinate plane, they form what's known as a system of equations. The system of equations defines the relationship between the two lines. They can have no points in common, 1 point in common, or infinite points in common. Graphing the lines on the same coordinate plane can help to determine the relationship. So we're going to start with graphing, and then we'll move on to algebraic methods for working with systems and other lessons. So the first thing we want to do is we're going to graph some pairs of equations on the same coordinate plane. Our first pair of equations is y equals negative 3x plus 5 and y equals 2/3 x minus 3. I'll graph this one in dark blue, and I'll graph the second one in red. We're already in y equals mx plus b format. M is our slope, and b is our y-intercept. So we start at our y-intercept. So we're going to start at 5. And then our slope is negative 3, which is the same thing as negative 3 over 1. So we're going to go down 3 and then over 1. And you can do this a few times if you want to get a nice pathway for your line. Or you can only just do it the 2 times if you want, because you only need 2 points to define a line. I'm going to do a lot of points so that I have a nice pathway to follow, since I'm not on regular paper and don't have a ruler. Let's try that again. So you want to follow the pathway of your lines, or your points, to make your line. Okay, the second one I'm going to graph in red. I have y equals 2/3 x minus 3, so I start at negative 3. And 2/3 tells me to go up 2 over 3. Then up 2 over 3, up 2 over 3, and then I can go backwards just to give myself enough points to follow for graphing the line. And I connect the dots. And of course, ideally you want a nice straight line, but so this tells us that these two lines have this relationship. They're intersecting. Okay. We have another set. We have y equals negative x minus 2 and y equals negative x plus 3. This time I'll graph the first line in red. I start at negative 2. I don't have a visible m, but that's an invisible 1. So my slope is negative 1, which is the same as negative 1 over 1. So I'm going to go down 1 over 1. Okay, to graph this line, because my slope is 1, I just follow the corners of the graph paper. Trying to keep it as straight as possible. And that's this line. My second line I'm going to graph in the dark blue, and I'm going to start at positive 3. And I have the same slope. I have an invisible 1, so my slope is negative 1 over 1. So I'm going to go down 1 over 1. And I'm going to follow the pathway of these points. Again, ideally you want a nice straight line. And the relationship between these lines is that they don't intersect. Those relationships tell us some things. First, we have parallel lines. And parallel lines do not intersect. They have absolutely no points in common. Therefore, there is no solution to the system. This is called an inconsistent system. Or you can have intersecting lines, such as these. They intersect in one place only, right here. The point where the lines intersect is the solution to the system, and this one appears to be 0, 2. Known as skewed lines, because they're not parallel or perpendicular. You can have perpendicular lines will also have one solution. If they're not parallel or perpendicular, though, they're skewed. And the single solution makes this relationship consistent and independent. You can have something called a coincident line. What happens with the coincident lines is you have two lines that overlap one another. So they intersect everywhere. They're known as coincident lines, and there are infinite solutions. Every point is a solution because they are touching everywhere. So I should say every point on the lines. The fact that there are infinite solutions makes this relationship consistent, dependent. Okay, so consistent means solutions exist. Inconsistent means no solutions. Independent means you have two different lines. Dependent means you essentially have one line. But that line possibly has two separate equations. If we want to graph the same pair of, or we want to graph some pairs of equations on the same coordinate plane, we're going to say how many solutions exist, whether the systems are inconsistent, consistent independent, or consistent dependent, and if there is a solution, we are going to name it. So here I have x plus y equals 3 and x plus y equals -2. I want to put these into y equals mx plus b format. So I'm going to actually pick this x up and I'm going to move it over, and that's going to make it negative. If I change sides, I change signs. I'm going to do the same thing over here. Okay, I have my first line starts at 3, and it has a -1 slope, so I'm going to go down 1 over 1. And as I cut through, oops, I lost my spot. That'll be my first line. My second line starts at 2, and it has a slope of -1 also. So I'm going to go down 1 over 1 along the whole path of this line. Now this system, we have parallel lines, so there are no solutions. No solutions. We are inconsistent. And since there are no solutions, we can't state it. For my next graph, I have y equals y equals 1/2 x minus 2. This one's already in y equals mx plus b. This equation needs to be rearranged. First, I'm going to pick up the x and move it. So I'm going to have -1/2 y is equal to -x plus 4. And I want to get rid of this -1/2, so I'm going to multiply the whole equation by -2. This -1/2 and this -2 will cancel, leaving me with y. -2 times -x gives me positive 2x, and -2 times 4 gives me -8. So graph my first line, I start at -2, and my slope is positive 1/2, so I go up 1 over 2. Then I'm going to go backwards. so that I can graph a nice straight line, because I'm looking for a solution, so I need to really ensure that my line is as perfect as possible. Again, this is when a ruler really comes in handy. Okay, for my second line, I start at -8. And my slope is +2, which is the same as 2 over 1. So I'm going to go up 2 over 1. Okay, so I'm going to graph this line. And you can see the point that the two lines have in common is right here. So we are consistent, independent, because we have two separate lines. We have one solution, and that solution is the point 4, 0, this point right here. Got two more examples. So what I would like you to do right now is to pause the video and then graph the lines, state whether the systems are inconsistent, consistent independent, or consistent dependent, how many solutions there are, and if you have one solution, name it. Okay, so I've graphed both systems. In the first one I had one solution, so that made it consistent independent, and my solution was -1, 7. Now in the second one, I didn't write these things down yet because I wanted to discuss it. When I solve this for y, so I get y equals mx plus b, if you look, I have the same equation twice. So I get one line. So the same line can be represented in multiple ways. This has infinite solutions, and that makes it consistent, dependent.